So far we have seen unsigned numbers and their representations, right? We can use decimal, octal, hexadecimal, everything. But generally we prefer binary representations because your computer is designed such a way that it can understand binary numbers clearly. Okay, right. But the problem is we have not discussed how to represent negative numbers, isn't it? So that's why we have to talk about how to represent sign numbers. Sign numbers means positive, negative, both. Okay. For that we use sign magnitude, ones complement, twos complement representations. Okay, now let me bring our computer into the picture, because so this entire story, why whatever we are studying, it's only because of this computer, right? Now we'll ask, my dear computer, so can you understand, integers? Yes, I can understand. But how do we know that, let's say, this computer understands that these binary patterns are integers? Very simple. So the computer is nothing but circuits, right? So if you give integer 2, integer 3 using some format, I don't know. Okay, we'll discuss that. Somehow if you give 2 and 3 to this computer, and if you ask that computer to do addition, then the output is 5. Okay, that means, of course, again, in the same format what we are assuming, that means some format is given as output, but we know that that is, let's say, representing 5. Whenever you give 2 and 3, if output is 5, then we say that your computer is understanding integers. That's why it was able to add them properly. That's it. So this is about, your computer understanding numbers, right? Now the second thing is, this computer is going to take the data integers and it is going to add them, otherwise subtract, multiplication. To perform the operations, then it is going to have circuitry. When it is having, example, let's say adder circuit, then this adder is designed such a way that it takes inputs, and that input is nothing but integers, and your adder will be designed like this. Okay, so data will be taken through registers. We will see that details later. So in the registers we are going to store the data. That's why we have to fix the size of the integer. If you have very large integers which cannot fit in these registers, then this adder cannot perform this addition function, isn't it? That's why we have to fix in computer. What is fixed is integer size is fixed. So now let's come to our concept. When you have signed numbers and we are going to represent them for, this computer, then this computer will fix the size of the, otherwise, number of bits in that integer. Okay, since we are going to use binary patterns only, then with that n bits, how many binary patterns we can generate? 2 to the power of n. Okay, remember it. So I am assuming that, let's say, your computer now supporting n bit integers, because it can take n bit integers and it can do manipulation. Then how many binary patterns we can generate? 2 to the power of n. Now let's begin the story. First thing, signed magnitude representation. In signed magnitude representation, for simplicity, first of all, I assume that, let's say, I am going to represent only using 4 bits. Okay, 4 bits, 1, 2, 3, 4. Then how many patterns can be generated? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, then 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, triple 1, then 1 followed by triple 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, correct? So everywhere 1. 4 plus 4, 8, 8. 16 patterns can be generated. Now since we have to represent negative numbers, so all the patterns which starts with 0 are given as, otherwise, fixed as positive numbers. This, all the patterns which starts with 1 can be, assumed as negative numbers. So this is the concept in signed magnitude representation. Okay, so now the interesting thing, if you see, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Now here this is minus, this will be value. Okay, so 0, 0, 0 is value 0, minus 1 represents negative number, 0, 0, 1 means 1, in that way, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. So this is about signed magnitude representation and their numbers. But if you see, one drawback I can say, 0 has 2 representations. Whenever there are multiple representations, so we will be wasting one representation, one thing. Second one, so there will be ambiguity. So because of this ambiguity, what happens is, so 2 representation for 0, right? Example, let's say in your computer, so your processor is comparing one variable x with, whether it is checking like this, x is 0 or not. Now this x can have two patterns, right? Maybe all zeros, otherwise 1 followed by all zeros. Then your circuitry should be designed such a way that it should check two times. First of all, it should check like this: is it all zeros? Second, is it 1 followed by 0 0 0? In any case it is going to be 0, correct? So I can say that rather than one comparison, here you require two comparison, so it may take more time, right? In that way. So because we are going to study computer organization with what motivation? With optimization motivation, correct? We have to optimize everything whenever it is possible. That's why if we have a chance, we have to avoid it. That's why in sign magnitude representation, that is treated as drawback. Okay, so one of the drawback is having two representations. Second thing, doing manipulations, like generally when you have numbers, what you do? You do addition, subtraction, multiplication, right? When you have sign magnitude representation, then addition, subtraction will be little bit difficult than other representations. Okay, we'll see the reason why it is little bit difficult here. So example, let's say you have one number which is positive number 0001, and you have a negative number something 1 followed by 11110. Example, let's say you are doing addition. Okay, take the second case 0101 0110. If they are positive numbers, then if you know that they are positive, then addition will be very easy. Add these two bits, we can have adder, right? So we will be studying full adder and half adder, don't worry. So using that, I can add these two bits, then I get 1, then after that 0 1 1, again adder I use here in that way. So 1 plus 1 0, here carry will be 1, that carry will be propagated to this one. So in that way finally we can do the addition, not a problem, without seeing the sign bits. If you know that these two are positive numbers, this will be the addition. What if one is positive, one is negative? Then blindly adding them, will it work? We'll see. 1 1 1 1. Okay, so 1 plus, what is this representation? Plus 1, right? This is minus this 6, correct? Minus 6 plus 1 is minus 5, but it is not minus 5. That means we have to change the addition model. Okay, fine, we will change, not a problem. But first of all, we have to see these two bits, right? So based on whether they are positive or negative, we have to decide the circuitry, correct? That's why it is little bit complex. It's not straightforward. Finally, I want to say, okay, it's not straightforward. So that's why sign magnitude representation is not used nowadays. Okay, remember it. So implementation is difficult because addition, subtraction will become little bit costly, otherwise I can say lengthier. Okay, they take little bit more time than here, 1 in 1's complement, 2's complement. You will understand that after studying 2's complement. Remember it now. Second thing is 0 has multiple representations. Now one interesting mathematical question here is, example, let's say you have n bits. What is the range of numbers you can represent with that n bits in using sign magnitude representation? First bit is definitely is going to be for sign bit, correct? So if it is 0, then how many other positions you have? N minus 1. So if it is 1, then it will be all negative numbers, then again n minus 1 positions. So with n minus 1 positions, how many patterns we can generate? 2 to the power of n minus 1. So here also with 1, 2 to the power of n minus 1 other patterns, correct? Because there are n minus 1 other positions. So what I want to say is, finally you have 2 to the power of n minus 1 plus 2 to the power of n minus 1, which is nothing but 2 to the power of n patterns. But out of them, 0 is using 2 patterns. That's why the number of numbers which are going to be represented, that means total distinct numbers which are going to be represented is 2 to the power of n minus 1, because 0 is taking multiple numbers. Second one, we will see the range. The range is like this. You are going to represent 0, isn't it? Yes. In the negative, what is the least number? Minus 7 for 4 bits. So to know the value, these last 3 bits are important, right? So with last 3 bits we can represent maximum 7. That's why least number can be represented minus 7. Similarly, when you have n positions, apart from the first bit, remaining n minus 1, with remaining n minus 1 positions, what is the highest number you can write? What is the highest number we can write? 2 to the power of n minus 1 minus 1, correct? And especially that is a negative number. So that's why it is the smallest. Up to maximum 0 1 1. That means 2 to the power of n minus 1, n minus 1 minus 1. Okay, so this is the answer. You just check it out. If n is 4, it would be minus 2 to the power of 4 minus 1. 4 minus 1 is 3. 2 cube 8. 8 minus 1 7. 2 2 to the power of 4 minus 1 2 cube, 2 cube minus 1 7, minus 7 to 7. This is a range of numbers which are going to be represented. The total number of patterns we are going to represent only 2 power n minus 1. Of course you have 2 power n patterns, right? Remember it. Now we'll come to ones complement representation. Okay, in ones complement representation, so what we are going to do, how we are going to represent negative numbers, we'll see. Let me take first of all 4 bits. With 4 bits, these are the patterns, right? 4 zeros, 0 0 0 1, 0 0 1 0, 0 0 1 1, 0 1 double 0, 0 1 0 1, 0 1 1 0, 0 triple 1. Okay, now 1 triple 0, 1 0 0 1, 1 0 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0 and 4 ones, correct? So 1 2 3 4 5 6 7 8, here 1 2 3 4 5 6 7 8, correct? Now first of all, to understand ones complement representation, you should understand what is ones complement concept. I will tell you. Ones complement in mathematics is like this. Example, especially that is for binary pattern. So when you have a binary pattern like this 1 0 1 0, then its ones complement is nothing but subtracting this 1 0 1 0 from all ones. That's it. Try to do it. 1 minus 0 1, 1 minus 1 0, 1 minus 0 1, 1 minus 1 0. Similarly, there is a nines complement also. Example, in decimal system, when you have a decimal number like 235, then what is the nines complement of this 235 is a number which is going to be got by subtracting this 235 from all the nines. 9 minus 5 4, 9 minus 3 6, 9 minus 2 7. This is called nines complement of 235. So for 764, what is the nines complement? Let's try. Subtract 764 from all nines. So 9 minus 4 5, 9 minus 6 3, 9 minus 7 2. So what is this 999, sir? What is the speciality? Simple. When you have 3 digits, then 10 is the base, then 10 cube minus 1 is going to be the number from which you are going to subtract 764 to get the nines complement. Okay. Now, sir, if I have 1 2 3 4, then what is the number from which we have to subtract to do the nines complement? If you want to do the nines complement, what you have to do is, we have to first of all find out the 4 positions, 4, right? Then 10 power 4 minus 1 is the number from which we have to remove 1 2 3 4. Then you get nines complement value of 1 2 3 4. That is simply subtracting 1 2 3 4 from 9999, because 10 power 4 minus 1 is all nines. So it will be easy. Now similarly, when you have base 2, we define ones complement. So example, if you have 13, what is the ones complement of 13? I will tell you. Example, let's say you are using 4 bits. Minimum 4 bits are required, isn't it? Okay, let's use 4 bits to represent 13. Then, so the formula for 2's ones complement is 2 to the power of 4 bits, right? 2 power 4 minus 1 is the number from which we have to subtract 13. So 2 power 4 16, 16 minus 1 15, 15 minus 13 2, right? So this would be the answer, 15 minus 13 2. But the same thing we can do in using this format also, like one more way. 13 represent in binary, 8 4 8 plus 4 12, 12 plus 1 13. Okay, so answer should be 2, right? Okay, but we have to subtract from 2 power 44 minus 1. What is 2 power 4 minus 1? 15. 15 is nothing but all ones. That's why we write all ones. Subtract now. 1 minus 1 0, 1 minus 0 1, 1 minus 1 0, 1 minus 1 0, correct? So 15 minus 13 is 2, right? So 2 is the dash complement of dash, 2 is the ones complement of 13. Understand? The beauty of 0 0 1 0 is, if this 0 0 1 0's ones complement will try again, we know that we have to subtract from all ones. 1 1 minus 1 0, 1 1. So you get it back, right? Ones complement of a number is that number itself. So that is the property which we are going to use to in this representations. Example, let's say you have a number 2. 2 will have 2's complement, 1's complement number, right? 2's 1 complement is x. The x 1's complement again 2, right? Like, then I can use this 1's complement of 2 as negative number. That means negative version of that number. Okay. So finally, what I am going to do is, example, when you have x, then I will find out 1's complement of x. Let's call it as x bar. Now I use x bar as minus x. Okay. If x is, let's say, some number, then minus x is going to be 1's complement of x. Such a way I am planning. Okay, don't ask me, sir, is it really universal truth? No, such a way we are defining the theory. What we are going to do finally, we take a number, any number, let's positive number, its 1's complement representation is going to be a, I can say minus x. Okay, we will see that. Example, for 0 0 0 0, it is, what is the, value of that? If I take value 0, right, then minus 0 will be represented by 0 0 0 0's 1's complement. What is that? 1 1 1 1. I will tell you one shortcut from now onwards. Whenever you have a binary pattern and you would like to know the 1's complement of that, you will be subtracting from all 1's, right? That is what the formula. Then directly, without that also we can directly do that. Simply do bitwise complementation. So the exact thing will happen. That's it. Okay, that's the result. That is the observation, I can say. Correct? Example, 0 1 1. Do like this. This is what actual procedure. Correct? So we have to subtract from 15. 1 minus 1 0, 1 minus 1 0, 0 1. This is exactly equivalent to this patterns. Let me remove this one. If I do bitwise complementation of 0 1 1, what you get? 1 0 0. Correct? Both are same. That's why from now onwards, let us use this shortcut. Now, what is the 1's complement of all 4 zeros? 4 1's, right? That will be represented as minus 0 from now onwards. Okay, 0 0 0 1 is 1. What is the 1's complement of this 0 0 0 1? It is nothing but 1 1 1 0. 1 1 1 0. This is going to be minus 1 in that way. Okay. Now, so 0 0 1 0. For that 1 1 0 1. Yes. So surprisingly, see, all these numbers, 1's complements are going to be these numbers, like in this order. So it would be minus 2. You can check it out. So this is minus 3. This is minus 4. This is a way we are just, imagining the things. That's it. Okay. This is now theory. Minus 5. This is one, I can say, idea. So for this one, 0, minus 0, minus 1, minus 2. I missed one thing. Let me write here. This is from now onwards minus 0. This will be minus 1. This would be minus 2. This is minus 3. This is minus 4. This is minus 5. This is minus 6. This is minus 7. Okay. Right. If you see one more thing. So again 0 has multiple representations. That is a drawback. Okay. That is one drawback. Now second one, when it comes to manipulations like addition subtractions, how to do addition subtractions we'll see. Let's see one observation. 0 0 1 1. You have one positive number and another positive number 0 1 1 0. Okay. Otherwise let's take 0 1 0 0. So 1 plus 0 1, 1 plus 0 1, 0 plus 1 1 0. Because these two are positive numbers, their addition, this is 2, this is 4. 2 plus 4 6. This is 3, sorry, 3 plus 4 7. So it's properly working. Now what about one positive, one negative number? We'll take one positive and one negative number. Let me take this one 6. Correct? This is 0 1 1 0. Second one minus 2. 1 1 0 1. So I am doing addition. So here one interesting thing I am just trying out. I don't know whether it works or not. I do simple addition. I don't see the symbols. Remember one thing. What was the negative point of sign magnitude representation? In that, first of all, we have to see the sign bits. Then in the second step, we have to do the operation. Correct? Because so your operation depends on the sign bit. So that's why we ignored it. But the beauty of 1's complement, you see, it is little bit better than sign magnitude, because just check it out. Do this addition, you will understand slowly. So this is 6, right? This is minus, just check it out, directly take it, 1 1 0 1 minus 2. 6 plus minus 2, if I do addition, I supposed to get 4, right? So let me do 0 plus 1 1, 1 plus 0 1. I am not seeing the symbols. Okay, blindly I am doing addition. 1 plus 1 0, 1 plus 1 0. Correct? So 1, 1, 1 plus 1, 0. You got end around carry, you see. Correct? 1 plus 1, 0. You got carry. Sir, what to do with this carry? Take and add here. You get surprising result. 1 plus 1, 0. 1 plus 1, 0. 1. Yeah, 4. So that is one beauty of this ones complement representation. That means, so you don't really require to check the sign bits directly. Take any two numbers and add them. But if you get end around carry, we have to add it again. Sir, is it not like, sign magnitude? In the sign magnitude, initially you checked signs first. You wasted your time, correct? After that you did addition, like in sign magnitude. But here also, rather than wasting initially, but simply you did addition, after that there is one extra step. What is that? Adding end around carry, correct? That is one drawback. So remember it. So just keep on observing. Slowly I will summarize. You don't know anything at this moment. I'm just checking out randomly patterns. Let's take 0, 1, 0, 0, 4. Let me take something around minus 6, which is 1, 0, 0, 1. Let's try again addition. What happens? 0 plus 1. This is 4. This is minus 6. Correct? So 0 plus 1, 1. Is it minus 6? Yes. 1, 0, 0, 1. So 0, 0, 0. 1, 0, 1. 0 plus 1, 1. 1, 1, 0, 1. So 4 plus minus 6, minus 2. So minus 2. 1, 1, 0, 1. Perfect. That means sometimes if you don't get end around carry, then automatically the result is correct. So now here, is it not advantage? Yes, definitely it is better than sign magnitude. In sign magnitude you have to see the symbols here. Based on that we have to perform the operation. There is no better way, but here we have a better way. What is that? Simple addition we can do without checking the symbols. If you get end around carry, then add it. That is the extra step. Let's work it out, these two. Let's randomly check it out. So 1, 0 this time. 1, 0, 1, 1, minus 4. Second one, let's take something plus 1. Minus 4 plus 1. 0, 0, 0, 1. Minus 4 plus 1 supposed to be what? Minus 3, isn't it? So let's do that. 1 plus 1, 0. 1 plus 1, 0. Then you get here 1. 1. 1 plus 0, 1. So I got 1, 1, 0, 0, which is minus 3. Perfect. Whenever you are not getting end around carry, that is directly the result. Okay. It's not only for these 3-4 examples. Remember, it works always. Okay. So finally, we understood what is ones complement representation and that how to do additions. Correct. So addition is like this. First, simply add like dash numbers, unsigned numbers. Correct. Unsigned. Then if end around carry, if there is end around carry, there is an end around carry, then add it to LSB bit. Correct. Next, second, if there is no end around carry, keep quiet. That means this step is unnecessary to write, right? So if there is no end around carry, don't do anything. Direct it's the result. So this is a process. Okay. But the only drawback is when there is end around carry, one more level. So finally our goal is improving your computer's performance. Correct. So when you do for simple addition, if you do 2 times, that means we have to do one addition followed by another addition, end around carry. So definitely there will be a delay. Correct. So if we have better procedure, then we don't use ones complement. So people used ones complement initially because there was no better procedure. But later what happened? Two's complement representations are proposed. So the advantage of two's complement is additions and subtractions all are one shot, only one addition. Okay, just observe that two's complement representation now. Okay, which is very popular, and we will see what are the advantages we have for that. Before that, let's try about subtractions. Okay, so in one's complement, if I do subtraction, what happens? We'll see how to do that. We will see. After that, we'll go to two's complement representation. Okay, now example, let me do subtraction. X minus y is generally means we are doing subtraction. Correct. So x minus y is nothing but, can I write x plus minus y? Perfect. Beautiful. Then x. Whenever you want to do subtraction, x minus y, then you do x plus minus y. Both are same, right? Now that means x, we have to do addition. Rather than subtraction, we can do addition. But before that, we have to take what? Minus y. So rather than y, we have to take minus y. Sir, how to get minus 5 in 1's complement representation? Recall. For any number, minus y is nothing but 1's complement of y, isn't it? Let's check it out. So I explain with one example. Example, we do 3 minus 5. Okay. So what is 3? 0, 0, 1, 1 minus 5. 5 is what? 0, 1, 0, 1. Right. So blindly apply that procedure. What is that procedure? Take 0, 0, 1, 1. Take 1's complement of 0, 1, 0, 1. So that would be minus y. So it would be 1, 0, 1, 0, 1, 0, 1, 0. Then do addition rather than subtraction. 1, 1 plus 1, 0, 1, 1 plus 0 plus 0, 1. So 0 plus 1, 1, right? There is no carry, right? End around carry. The end around carry is nothing but which comes from this addition. No, I didn't get any carry. So that's why 1101 is the exact answer. Check it out. 1101 minus 2. 3 minus 5 supposed to be minus 2. Perfect. So if you have doubt, one more time. Let's take randomly 4, 0, 1, 0, 0 minus, let's do this one, 1, 0, 1, 1. Otherwise, let's take 4 minus. So why I am not taking minus 5, I will tell you. If I take minus 5, 4 minus minus 5 are supposed to be 9, correct? But 9 cannot be represented because with our numbers, we can only represent up to 0, minus 7 to plus 7. Try to understand. So that's why, so 9 cannot be represented. So you get wrong answer, however. That is called overflow. Remember it. I am going to discuss that overflow. Sometimes when you do addition or subtraction, then the result will be, out of the range. When you get out of the range numbers, we say it is overflow. So let's take minus 6 minus 6 minus whatever you do, then it will be, let's take minus 1. Minus 6 minus minus 1 will be what? Plus 7, correct? So that is representable. We'll see whether it is possible or not. Minus 6, x minus y. How to do x minus y? In our procedure, take x minus 6, 1, 0, 0, 1. Take y. What is y here? Minus 1. But 1's complement of that. 1, 1, 1, 0. 1's complement is 0, 0, 0, 1. Then do addition blindly. 0, 0, 0, 1. 1 plus 1, 0. 1, 1, 0. 1, 0, 1, 0. So what is 1, 0, 1, 0? Minus 5. So minus 6 minus minus 1 plus 1. Minus 6 plus 1 is what? Minus 5. Perfect. So in that way, so addition subtractions can be done using 1's complement representation. Now I have forgotten to tell you the range of these 1's complement numbers. If you see here, it will be minus 7 to plus 7, correct? So I can say that the range is minus 2 to the power of n minus 1 minus 1 to 2 to the power of n minus 1 minus 1. It's quite easy to understand that because when you have n positions, the first bit is going to be for sign, correct? So we are representing positive and negative. So when you are representing positive and negative, then definitely with this n minus 1 bits, how many numbers, how many patterns we can generate? 2 to the power of n minus 1 minus 1, right? So 2 to the power of n minus 1 minus 1 patterns are positive. Some other 2 power n minus 1 minus 1 are negative, correct? So that's why minus 2 to the power of n minus 1 minus 1 to 2 to the power of n minus 1. That's it. Okay. So this is about 1's complement representation and problems, right? So what are the important problems you have seen in 1's complement representation? One is end around carry. When there is end around carry, there will be delay because we have to add that further, right? Second thing, if you have, that means, your 0 has two representations, then again there is a confusion. Already I told you, because of that confusion what happens, then example, when you are comparing your variable with 0, then x will be checked 2 times. First of all, this 0 will be checked against this pattern, and after that this pattern. It will be definitely a little bit, I can say, inefficient. If you have only one representation, then it takes only one comparison. Here you require two comparisons, I can say, right? That's the problem. And we'll go to 2's complement representation now. This is very famous and people use now 2's complement representation. The reason is, so there is no end around carry, first of all, like 1's complement representation. Second thing, you don't have multiple representations for 0. So all the problems are avoided by 2's complement representation. Let's see that. Okay. Now we'll see 2's complement representation. In 2's complement representation, we give negative weightage to the last bit. Okay. That means minus 2 to the power of 3. Example in these 4 bits. So that what happens, this positive, I mean this binary pattern where the last position is 0, its value will not be changed. You see 0 1 0 0. In unsigned numbers, what is the value? 4, right? Here also it would be same because weightage is same, 2 power 0, 2 power 1, 2 square, but minus 2 cube into 0 will be 0, like plus 2 cube into 0. So that's why there is no difference here for these values. So that's why these numbers are going to be representing 0, 1, 2, positive 2, positive 3. That's why we can use these patterns for positive numbers 5, 6, 7. Now these patterns, see, because of here 1, it would be minus 8 plus remaining weights are positive weights. Minus 8 plus 0, minus 8. This is going to represent minus 8. So this would be minus 8 plus 1, minus 7. Minus 8 plus 2, minus 6 in that way. So remaining numbers will be represented minus 5, minus 4, minus 3, minus 2, minus 1. So here there is only one 0, positive 0, no negative 0. Okay. That means finally there is only one 0 we have. Second thing, the beauty of this second 2's complement representation is, so here this is having a strong mathematical background, like number theory, especially arithmetic modulo operation. We are not going to discuss that all the details, but we'll see the result of that. Result of this, what happens is, when you add any two numbers, then automatically the result will be correct. So example, let's say you have 0 0 1 0, which represents 2. Okay. Now one more thing is 0 1 0 0. Since they are positive, 2 plus 4 supposed to be 6, then this addition will work, right? So you get the right answer, not a problem. But why it works for positive and negative, we will see. Let's take one positive number which is 3 and one negative number. So 3 plus another number which is negative, I am taking minus 5, 1 0 1 1. Okay. So 3, what is 3? 0 0 1 1. So minus 5, 1 0 1 1. Correct. So this would be the minus 5. Just blindly add them first. 1 plus 1, 0. You get here 1. 1 plus 1 plus 1, 1. So 0, 0 plus 1, 1. 1 0 1 0. Right. So actually we did a mistake here. 1 plus 1 plus 1 is 1. Then you get carry actually. 1 plus 0, 1. It would be 1110. Okay. So 1110 is nothing but, you see here, minus 2. So 3 plus minus 5 is minus 2. So second thing, we'll see one more. So minus 6 plus something we do 2. Minus 6 plus 2. It's supposed to be minus 4 and representable. If the number, the result is not representable, you get overflow. We will see that overflow problem, but I'm not. So I'm taking the number such a way that there is no overflow first of all. Minus 6 plus 2, minus 4 is representable, but your simple addition will work or not, we'll see. Minus 6, 1 0 1 0 plus 2, 0 0 1 0. Correct. So it would be 0 plus 0 0, 1 plus 1 0, 1 1 1 0 1. Yes, 1 1 0 0. So it would be this one, minus 4. Perfect. So it's working. Correct. Now one more example we'll see. Let me take 1 1 0 0, whatever it is randomly, 1 0 1 0. What is this 1 0 1 1 0 0? Minus 4. Correct. This is minus 8 plus 2, minus 6. Definitely it is not representable. You get wrong answer. Okay. That's fine. Ignore that. So let's take negative number and one positive number. So let's take this one, 7 0 1 1. When you take one positive number, one negative number, you never get overflow. Why? Because I will tell with example. In this case, it would be minus 6, right? This is plus 2. Okay. So these are all, let's say, representable numbers in our model. Okay. Which highest number is lowest number is minus 8, highest number is 7, right? Now your minus 6 is somewhere here. That negative number which you are going to take in the addition is here, and the positive number is here. When you add minus 6 plus 2, then the result will fall in between here, because question number 1, For minus 6, if you add any positive number, the result should be this side first of all, right? Second thing, since with respect to this number's perspection, so when we are subtracting something, see 2 plus minus 6 means we are subtracting something from this one, then the result supposed to be this side. So since minus 6 says that because some positive number is added to me, then the result should be this side. Then this 2 says that since something is subtracted from me, the result supposed to be this side. When both conditions are satisfied, then that should fall in between minus 6 and 2, right? So that's why you never get overflow, right? So that is the concept, remember it. But when you add two positive numbers or when you add two negative numbers, you are going to get the overflow, right? Remember it. Now apart from that, so is it correct? That means simply adding it, will it work? We will see. So finally, the question is all about how to do addition of 2's complement numbers. Example, let's say I have two numbers 2 plus minus 5. Then I would like to add. 2 is one number, minus 5 is another number. I would like to add them. So what is the technique, sir? Finally, simple. Take the representations in the 2's complement form. So 2, 0, 0, 1, 0. Blindly add them. Don't worry about anything. Minus 5, 1, 0, 1, 1. Sometimes you get end around carry. Okay. So when you get end around carry, simply discard it. Still the result is correct. 0 plus 1, 1. 1 plus 1, 0. 1 here. 1. 1. 1, 1, 0, 1. Minus 3. 2 plus minus 5, minus 3. In that way, it's correct, giving the correct answer. Second thing, let's take something randomly, one more. Minus 7 plus 4. Minus 7, 1, 0, 0, 1. Plus 4. What is plus 4? 0, 1, 0, 0. Let's try this. 1, 0, 1, 1. 1, 1, 0, 1. Minus 3. Perfect. In that way, so always this method works. 2's complement addition is very easy. Take any two numbers and simply do like unsigned addition. In unsigned addition, whatever the way you do, in the same way you do. That is one thing. If you get end around carry, please discard it. Okay. So that is about second 2's complement representation. Now we'll see the plus points over 1's complement representation. So if you compare 2's complement and 1's complement, you understand that. So the drawback of 1's complement is 0 has multiple representations. Second thing, sometimes you have to do extra step, right? That is adding end around carry. That's why. So 2's complement addition is faster than 1's complement, right? Similarly, subtraction also we can do. Sir, how to do subtraction? Subtraction is very simple. X minus y you want to do, right? But I know how to do addition. With that addition we can implement minus also. How? X minus y is x plus minus y. Here also x as it is plus, we know how to do addition, just now we have discussed. Then take the 2's minus y. What is minus y? Minus y is nothing but here. So negative 2's complement version of y, correct? So rather than taking y, you take minus y. So how to get minus y when y is given, I will tell you. So in this model, just observe the relation between a number and its 2's complement, negative version. Example 4 minus 4. So the difference between these two, that means how to arrive to minus 4 is take 0, 1, 0, 0. So the question is like this, given a number, how to get its negative version, okay? So 0, 1, 0. First of all, apply 1's complement. That means apply bitwise complementation, 1, 0, 1, 1. Then add plus 1. So 1 plus 1, 0. Then you get here 1. 1 plus 1, 0. You get here 1. So then 1, 1, 0, 0. See, minus 4. So from now onwards, so given a number, how to find out the negative version? For that means apply that 2's complement. So how to apply 2's complement? The formula is 1's complement plus 1. Remember it. 2's complement equal to, for any number, equal to 1's complement plus 1. That is the result. Example, I would like to find out just blindly 2's complement of 4 ones. 2's complement of 1, 1, 1, 1 is, it's an operation first of all. Forget about number system representations. We are using that 2's complement concept to represent negative numbers. Forget about that. The question is, there is an operation called 2's complement, okay? Mathematically already it is defined like 1's complement, okay? So what is the 2's complement is? Simply apply 1's complement and add plus 1. For 1, 1, 1, 1, 1's complement is 0, 0, 0, 0, add plus 1. So what you get? 0 plus 1, 1. 0 0 1. Just check it out. What is that 0 0 0 1? 1. So what is 1 1 1 1? Minus 1. Minus 1's 2's complement operation gives you plus 1. So that is the way this 2's complement is designed. Okay. Now let me tell you one important point. So these binary patterns are divided into positive and negative such a way that for any numbers 2's complement value is assigned for its negative version. That means example, there is a binary pattern for x, then for negative number, otherwise for minus x, 2's complement of x is assigned. That is the way we planned. Okay. Now one more beauty of this manipulations are any numbers 2's complement is again same number. Let's check it out. 2's complement. So that example 1 1 0 0, for that we do 2's complement 2 times. So if you do that first time, so apply bitwise complement 0 0 1 1, add plus 1, 1 plus 1 0, 1 plus 1 0 1, 0 1 0 0. Then again you do it 0 1 0 0, 2's complement 1 0 1 1. Then add plus 1, 1 plus 1 0 1, 1 plus 1 0 1, 1 1 0 0. Yes, you got your number back. So now this is very important point. What is that? The numbers are divided into two parts, your binary patterns, such a way that if some value is given for one binary pattern, and for that, example, if one binary pattern is given for x, its 2's complement is going to get minus x value. Such a way it is planned. Okay. See now, definitely 5's negative value is what? That means minus 5, right? Minus 5. Where is minus 5? So 0 1 0 1 1 0 1 1. The relation between the two is actually 0 1 0 1's 2's complement is 1 0 1 1. Just check it out. It's an operation. 0 0 means 1 0 1 0. Add plus 1. Okay. Now 1 1 0 1 1. Yes, understood. So this is the relation between positive numbers and negative numbers. For every positive number there is a corresponding negative number, and for whatever the pattern you have for some positive number, and its 2's complement is representing the negative number of that corresponding number, right? So that is one important point. That's why I am repeating so many times. Correct? Second, there is a difference between 2's complement operation and 2's complement representation. 2's complement is an operation first of all. So for any number, if you apply the 2's complement operation, you get another number. Okay. So that patterns, example, you have some positive patterns, you see. For them, if you apply 2's complement operation, you get another pattern. So they are assigned for the negative numbers in the 2's complement representation. Okay. So these two are different things. 2's complement operation is a usual mathematical operation, and 2's complement representation is about there is a computer and you want to represent positive numbers and negative numbers using some system. Then we are using 2's complement operation and we are creating a system called 2's complement representation, that we are discussing now. So finally you understood how these numbers are arranged. Second thing, so since in this 2's complement representation, when you have numbers, then if you want to do subtraction, what we have to do? Take x and minus y. For that, x plus minus y. So already we know that. Now you have strong idea about what is minus y. Minus y is nothing but 2's complement of, in this model. So minus y is nothing but 2's complement of y. Such a way it is designed so we can get it. Right? So then after that do the addition. Now we'll see one example. Example, when you want to do subtraction of any two patterns. 0 1 1 minus all ones. Okay, not all ones, let's say. Let's take not 0 1 1. Let's take 0 0 1 0, because overflow should not occur, right? So 0 0 1 0. Let's take 1 1 1 1. The question is how your computer can do subtraction. Simple. Using adder circuit, your computer is going to do, subtraction. How? First of all, your computer takes 0 0 1 0 into one register, let's say. Second, your computer takes 1 1 1 1 into another register, 1 2 3 4. Then your computer performs 2's complement operation for this number. Why? Because X minus y is nothing but x plus minus y. If you really want to do addition rather than subtraction, then we have to take minus y instead of y. But we know that we have y. Given y, we know what is minus y. Minus y is nothing but 2's complement of this y. So that's why. What is 2's complement of 4 ones? Let's do that. Your computer is going to do this one first. 1, 0, 1. First bitwise complementation will be done. Then 1 will be added effectively. So 0 plus 1, 1, 0, 0, 0. So finally, first your computer somehow gets 0, 0, 0, 1. Okay. Further there will be circuitry, don't worry. Then after that addition will be done. So there will be adder circuit. So that adder circuit is going to take this as input, this as input. Now it is going to perform the result, right? So the result will be like this: 0, 0, 1, 0, 0, 0, 0, 1. Don't worry, I am going to teach you how to design a circuit so that this addition, whatever the operation we are doing, that can be done. 0 plus 1, 1, 1 plus 0, 1, 0, 0. Okay, so it is 0, 0, 1, 1. So this is your adder. So this is 3, correct? Perfect. So 2 minus minus 1 is 3, we got it, correct? The only thing you don't know, sir, how to design this adder circuit. Okay, we will be studying that. Okay, so we will be studying ripple carry adder, second one carry look ahead adder. These two things I will teach you because these two are important for us. Okay, so this is about 2's complement representation. Let me summarize. In 2's complement representation, first thing, so for any pattern, negative number is nothing but that pattern's 2's complement. For any negative number, the corresponding positive number is nothing but 2's complement of that number. That is done. Second thing, additions and subtractions are easy, right? So with same adder circuit, we can do additions, subtractions, right? If we want. Next. So the third thing is, we don't require, another, whenever you are doing addition, okay, whenever you are doing addition, then simply whether it is one is positive, one is negative, or irrespective of their signs, directly add them like they are unsigned. Automatically you get the right result. That is one advantage of 2's complement. Whereas in 1's complement, so we have end around carry, sometimes we have to add it. That's why. So 2's complement representation is definitely better than 1's complement. Sir, why can't we use sign magnitude representation? In that also there are two levels. First of all, we have to compare the signs. Based on that, we have to do the addition, subtraction. That's why. So that would be difficult part. So circuitry wise, otherwise implementation wise, when you represent your numbers in 2's complement format, so additions will become easier. That's why people use 2's complement representation. The only thing I can say over in 3, the only disadvantage is having uneven distribution. You have 0 to 7, but here minus 8 to minus 1. See, there is one extra negative number in this representation. That means, so it is little bit biased over negative side. But whereas if you see 1's complement, that's not a big disadvantage, don't worry. But if you see 1's complement and this sign magnitude, the numbers are equally distributed. That is one thing. Now we'll see the range of numbers in 2's complement. In 1's complement already we have seen. In 2's complement we'll see now. So first of all, observe here so that easily we can understand. Positive. All the first bit is 0, then all are positive, right? Not positive, 0 and positive. So your range is, I'm just talking about now non-negative numbers. Let me write non-negative numbers. Non-negative numbers are 0 to, the highest number is with last 3 positions, right? 7, which is nothing but 2 to the power of n minus 1 minus 1. This is about non-negative numbers. So how many negative numbers we have? For negative numbers, we have these patterns where first bit is 1. So how many patterns we have? 2 to the power of n minus 1, isn't it? So all these numbers are going to represent minus 1, minus 2, minus 3, so on. Example, if you have 100 patterns, then how many negative numbers we can represent? Since you are starting with minus 1 up to minus 100. That's why I can say the negative numbers which are represented by this one is from minus 1 to 2 to the power of n minus 1. Sir, here why you got 2 to the power of n minus 1 minus 1? Why you got here 2 power n minus 1? Because we sacrificed one number for 0. Correct? Here, that's why 0 to 2 power n minus 1 minus 1, the total numbers are 2 power n minus 1. Now here also minus 1 to 2 power n minus 1, the numbers are, sorry, minus 2 power n minus 1. The patterns are 2 power n minus 1. Here patterns. So finally, when it comes to range, the range will be minus 2 power n minus 1 to highest 2 power n minus 1 minus 1. Let's check with n value 4. You can understand. Right. Let us talk about sign extension. Sometimes your processor wants to move some data from smaller size array to bigger size, otherwise smaller size register to bigger size. Example, this one. So forget about first of all sign extension. Generally, when you have unsigned numbers, so how you are going to do it? So is there any problem and how you solve it? So here, if it is unsigned numbers, then it would be value will be 8 plus 4 12, 12 plus 2 14, 14 plus 1 15, correct? So you have a value 15 and you want to move it to a bigger register. Then simply write 1101 here. I am assuming that my data is integer, unsigned integer. Then simply write all zeros here. Then automatically this value also will become 15, correct? So because the weight of this one and this one and this one and this one is not changed. So that's why there will not be any problem. But when it comes to signed numbers, that means you have negative numbers and positive numbers. In that case, there will be a danger. What is that? We will see. Example, assume that it's 2's complement representation. When it is 2's complement representation, this is negative number and the weights are like this, minus 8, 4, 2, 1. The value is minus 8 plus 4, minus 4, minus 4 plus 1, minus 3. Correct? This minus 3, when it is represented here like this, 0, 0, 0, 0, then it becomes positive number, right? So that's a problem. So if I write ones, then how many ones we have to write? I don't know anything, because if I write all ones, then what if I get a different value than minus 3? Then I am not representing the right number. That's a problem. But fortunately, your 2's complement numbers are having a property. So that is, I am going to teach because of that. So we can directly extend the sign. I will tell you that property. First of all, let's understand it as a result. Whenever you have a 2's complement representation, see the sign bit. If sign bit is 1, then write remaining all bits ones. If the sign bit is 0, then remaining bit should be 0. Such a way you write it. Automatically that will become correct answer. We will see the details later, but at this moment, so this concept is called sign extension. Okay, 2's complement, in that 2's complement, so we can extend the sign, right? That's why, so it will be like this. And one more thing, if it is 0, then this is positive number. For positive number, we know that, so by writing all zeros, it will give the correct answer. Only for negative numbers also it will work. So only thing we should do is extend the sign. The reason I will tell you. Example, let's say you have some number which is like this, 1 followed by something, okay, whatever that number. So when you have this kind of number, it is negative number, correct? Example, it's this is nth bit. Then what is the weightage, what is the value of this one with respect to 2's complement representation? So already I told you, for last bit the weight will be minus 2 to the power of n, okay? So sorry, minus 2 to the power of n minus 1, right? For 4 bits this would be minus 8, that means minus 2 cube. So minus 2 whole power n minus 1, okay, not whole power, minus 2 power n minus 1, 2 power n minus 1. So plus something. So this based on the pattern, you know, we will be having some value, whatever it is, minus 2 power n minus 1 plus value which you are going to get because of this pattern, right? Example here, this would be minus 8 plus some value, correct? What is that value? That value is nothing but 4 plus 1, doesn't matter. Let's treat it as value. Now, what if you have same thing, if I extend here 1, that means if I add one more 1 to this existing one, then what is going to happen? We will see. Initially we had 1 followed by something, okay, something here. So the answer for 1 followed by something is nothing but minus 2 power, this, let's say this bit is nth bit, then minus 2 power n minus 1 plus here you get some value, you know the manipulations, everything, correct? Now if I add, so this entire part is same like this one. Example, this is nth bit. Now let me add n plus 1th bit, especially I am adding 1 here. If I do that, then the value will become minus 2, you know that, right? Minus 2 whole power, this time because it is n plus 1th bit, it would be minus 2 whole power n plus this one. Because of this one, what happens? What is the weightage of this one? 2 to the power of n. You know one thing, the last bit will get negative weightage, remaining are positive weightages, right? So 2 power n into something 1, right? plus what about this value? This value will be like this value, right? Value. So now let's compare this value and this value. It is minus 2 power n minus 1 plus value. Here it is minus 2 power n plus 2 power n into 1 plus value. Okay. So value will be same, cancelled. You have minus 2 power n minus 1 here, minus 2 power n plus 2 power n. Let's simplify it. Can I write minus 2 power n as 2 into 2 power n minus 1? Yes. And one more thing, this is actually n minus 1 because nth bits, this is nth bit, then the weightage will be 2 power n minus 1. So minus 2 into 2 power n minus 1 plus 2 power n minus 1. If I simplify, 2 power n minus 1 common. So you will understand the reason for that. So minus 2 plus 1. Minus 2 plus 1 minus 1. So minus 1 into 2 power n minus 1 minus 2 power n minus 1. See, you have minus 2 power n minus 1, here minus 2 power n minus 1. So by adding extra 1 to the existing pattern, when you have already 1, then why if you add one more 1, there will not be any change in the answer. That is why we can extend to any number of ones, right? So let me show with one example. 1 1 0 1. Okay, since there is a 1, its weightage is minus 2 cube, correct? Now this value, whatever it is, let's say all these people are going to have positive weights. Okay, let's say that is 5 here especially. Now if I extend it to one more, like 1 followed by 1 1 0 1, because of this one, it is going to get 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, minus 2 power 4, and this one is going to get now positive weightage, 2 cube. It used to have minus weightage, but here positive weightage. But remaining things, this 101 won't get affected, you get 5, same calculation. So what I want to tell you is minus 16 plus 8, if you do minus 8, here minus 8 we have, plus 5, here also plus 5, so there will not be any difference. We can extend this to anything. Example, if you have 4 ones like this, followed by something 0 1 0, then this weightage is 2 plus 2 power 0, 2 power 1, 2 square, 2 cube, this is 2 cube, 2 power 4, 2 power 5, 2 power 6. Okay. Now here you have 4 ones, right? Take only 1 1 followed by 1 0 1 0. There will not be any change. These two will have same answer. Why? We will see. It is, what is the weightage of this one? 2 cube, right? Minus 2 cube plus 2, correct? If I convert it into decimal using 2's complement model, it would be minus 2 cube plus 2. See this one. This is going to get negative weightage, minus 2 power 0, 1, 2, 3, 4, 5, 6, minus 2 power 6 plus 2 power 5 plus 2 power 4 plus 2 cube. Just simplify this part, you understand. 1, 2, 3, 4, 1, 2, 3, 4. Minus 64 plus 32, minus 32. Minus 32 plus 16, minus 16. It's like having minus 16 directly. Minus 16 plus 8, minus 8. You get it again, right? That's why sign extension works for 2's complement numbers. Remember it. So this can be used as shortcut for solving some problems. Sometimes in GATE, they ask some questions like this. Which of the following numbers is divisible by 1, 1, 1, 1, 1, 0, 1, 1? Okay. So the question, of course, it is given as 2's complement numbers. Okay. Numbers are in 2's complement representation. So they did not, I did not mention in the question, but it is mentioned already in the question. Otherwise, we don't know, right? Now the question, which of the following numbers is divisible by this 2's complement number? Since it is 2's complement representation, so what is the value of it? 1 1 1 1 1 0 1 1, right? There are two techniques. First technique is find out the value using the weightages. How to convert it into decimal? It is a weighted system like binary. Only thing is you get here negative weightage. Okay, 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. Model number 1 I am teaching you first. 128 minus 128 because negative weightage plus 64 plus 32 plus 16 plus 8 plus 2 plus 1 3, right? Now if you simplify, minus 128 plus 64 minus 64 plus 32 minus 32 minus 32 plus 16 minus 16 minus 16 plus 8 minus 8 plus 3 minus 5. Finally you end up with minus 5. Rather than doing all these calculation, we can save the time, because in some questions they can give you bigger length string, correct? So that's why I use the shortcut. Because it's a 2's complement number, so any number of ones does not add any effect, we can cancel them, only leading one is enough, right? So 1 0 1 1, it would be minus 8 plus 3. minus 5. So finally I got the value of it. So same sign extension we can apply here also, right? So if you don't do that, unnecessarily you waste the time. Cancel the all the leading ones. So now first of all focus here. Which of the following number is divisible by this minus 5? So what is the value of this one? 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, minus 2 power 5, minus 32 plus, see this is 7, correct? Triple 1 means 7. So minus 32 plus 7, minus 25. Yes, it is divisible by minus 5. So which of the following number is divisible by, let's say really the question is divisible by minus 5, A is divisible. See this one, 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, which is minus 32 plus 4, minus 28, which is not divisible, cancel it. Now see, so if I cancel the first one, so remaining thing if you see 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, minus 64 plus this one, what is the weightage of this one? 0, 1, 2, 3, 4. So 16, minus 64 plus 16, minus 48 I think, minus 48 plus 7. Minus 48 plus 7 if you do, minus 41, which is not divisible by minus 5. We can cancel it. Of course, already A is the answer. Now see, we are checking it. So here 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7. We can cancel this one. So minus 2 power 6. This bit we can take directly. Plus this value 0, 1, 2, 3, 4. That means 16 plus 8 plus this one is 2 plus 1. 24, 26, 27. So minus 64 plus 27. It would be 37 I think, right? So it is also not divisible by minus 5. In that way we can solve this problem. So the trick here is to save the time, apply the sign extension technique. Okay.